Hello, everybody. My name is Masood Olia, and I'm a professor in the School of Engineering at Wentworth University. And I'm here with a problem related to kinetics of rigid bodies and related to mass moment of inertia and calculation of forces needed to bring a rigid body to rest. So why don't we get started? And I hope as you enjoy this video, as always, I would appreciate if you like the video and join my channel. Thank you. So let's get started. So you see in this problem we have this. So basically this is a brake system. So we have a disk that has a mass moment of inertia of 2 pound-foot-second square. See, that's the unit of mass moment of inertia in the US customary system of units. In the metric system, mass moment of inertia has units of kilogram meter squared. But in the other system is slug, feet squared, which actually, slug is rarely used. It's really, slug is pound, which is the weight divided by, acceleration. That's why you end up getting pound-foot-second squared times feet squared, which eventually becomes pound-foot-second squared. Just wanted to, clarify that. All right. Why don't we get it started? So we have the mass moment of inertia. So that's I. This is for what? For basically combination of, whatever is attached to this guy, to the drum. So that's 2 pound-foot-second squared, right? If the drum is initially rotating at 20 radians per second clockwise, so it's rotating like that. So that's the initial angular speed, right? It says determine the force exerted by the hydraulic cylinder, BC. So this force, what force should be applied here? We call it FBC, that hydraulic cylinder. Basically, that comes from let's say if this was a brake system in the car, kind of, it would be the force that you are exerting on the brake pedal. Of course, you can't exert really large force, so that's why you have the electronic system that will magnify the force for you. Okay, so what should be this force? So our objective is to find FBC, right, in order to stop the drum after it has gone through 20 revolutions. So, of course, this is not a good brake system. Imagine if this was a brake system of a car, 20 revolutions is not good. You want your system to come to rest maybe in quarter of a revolution or even smaller than that. But anyways, for the sake of doing a problem. Now, be careful that 20 revolutions has to be converted to the radians. So we say, okay, 20 revolutions, 1 revolution is what? 2 pi radians, right? So we go ahead and this becomes 40 pi radians. Now, the reason I converted that, because you see your omega is in radians per second. All right, so it's basically this problem has 2 parts. One part is kinematics, for which, given the initial angular speed, right, and you want the final angular speed to be what? 0. You want it to come to rest, right? And you know the distance or the number of the radians that this is going to go through. So assuming that this is a constant angular acceleration, and I'll explain why it's a constant angular acceleration, then we can go ahead and say, okay, look, in kinematics, one of the equations independent of time is this equation, useful equation. So if we set that equal to 0 and final angular speed equals 0, you can go ahead and solve for alpha by using this formula, right? Or rearranging the equation, basically. So initial angular speed is 20 squared divided by 2 times, and that's why we had to change this guy to radians. So if you do the calculation, I believe that becomes negative 1.5915 radians per second squared. So negative means basically deceleration. So even though this guy is going in this direction, but its alpha is the other way, right? Is it slowing down? Because you have to slow it down. You have to decelerate in order to come to rest. Okay, so that's the kinematics part, guys, getting the alpha. Now, kinetics part actually consists of two parts. The part that, I should say, dynamics and statics. Kinetics is the part that we try to figure out what forces are developed here between the pad and the drum. And once we calculate those forces, then the problem becomes a static problem. And we look at its effect on this part, okay? So let's get rid of that. All right, so let's draw a free body diagram as you do problems with kinetics. So let's say this is the free body diagram of the drum. Notice that nothing is mentioned about the mass of this guy, mass of the drum, right? So, and we don't need that because when you draw the free body diagram, yeah, you have the weight of this guy. I'll put it right in the middle here. You do have some reactions developed here, call it dx, dy, which we don't care about. And remember, this guy now is rotating. Its alpha, at least, is counterclockwise, right? So what forces are developed here? You see, as this guy rotating clockwise, the force of friction here would be opposing the direction of motion. So as it goes up, the friction force would be down. So this is the friction force of friction. And there's a normal force. I'm sorry, I got to put it on this side. I'm looking at the picture the wrong way. Right, so this is the force of friction, which is coming down, right? And this is the normal force that the pad exerts on the drum. All right, so remember now, alpha magnitude is 1.5915 radians per second squared, but the direction obviously is counterclockwise. So you see, if you take moment about d, and the major equation for kinetics is what? The moment equation. Moment about d, that should be equal to I, the centroidal mass moment of inertia times alpha. So if you take the direction of rotation as positive, which is this direction, right? You see how the only force that has moment about d is just the friction force. N passes through that, and all these forces are acting at d, right? So go ahead, the moment of the friction is friction. This is where you have to be careful. And you see that's going counterclockwise, which is consistent with the direction of alpha. That distance is 10 inch, but has to be changed to feet. Because look at the unit of I. See that? So that's 2 pound/foot second square times alpha, which is 1.59. So now you just put the magnitude because direction is already incorporated into the equation. So friction force from here, I calculated it to be about 3.82 pounds, right? And once you have the friction using what? The kinetic friction is kind of blurry there, but that mu k is 0.3. So since friction force is what? Mu k times n, therefore n, which is the normal force, and I need that, is friction divided by mu k. So that would be 3.82 over 0.3, which you get about 12.73 pounds. Now the problem, so this is the kinetics part related to the dynamics. Now the last part is drawing the free body diagram of this piece, which is really a static problem. So if you look at the free body diagram of that, and remember the objective is to find this force in this hydraulic cylinder, right? Which I call it FBC. So remember, hydraulic cylinder, they act like as if they are two force members, right? And remember, there's a pin here at A, which we really don't care about because we're going to take moments about that. So pin reaction AX and AY, right? And then now look at what you have to be careful. You see these forces here, the friction force, this is the force that the pad exerts on the drum. And this is the force, normal force that the pad exerts on the drum. The effect of them, when you want to put it right here, would be in the opposite direction. So friction force that is down here, sorry, I keep using the eraser by mistake. All right, so the friction force that is acting down is going to act up, and that's what, 3.82. We have those values. And the normal force that is acting to the right, now it's going to act this way. And then as you can see, this is really a static problem, right? All you have to do is to take moment about A, say it equal to 0. You have all the dimension. This is like, for example, 6 inches. This, I believe, is 12 inches. We have the picture right there. And this is also 6 inches. By the way, as you use moment equation, F times D, the unit is not important here because you're consistent, you're multiplying pound by inch. But here we had to be careful, right? Because of the unit of the mass, moment of inertia. All right, so moment of FBC about A is FBC times 6 inches going counterclockwise. I took counterclockwise to be positive. Then we have the moment of 3.82, the friction force, which is times 6, also going positive also, but the moment of the N, 12.73 times 18 going negative direction. So therefore, the hydraulic force that we need is about, let's see, I have calculated it here, it's about 34.4 pounds. Of course, this was your foot that is trying to apply to the to the pedal. You can't probably put 34 pounds. So as I said, that's where the electronic system come in to boost the force for you, to amplify the force. Okay, guys, again, thank you very much. I appreciate you liking the video and subscribe to my channel. I'll be back soon with new videos. Thank you again and see you soon.